So recording is now on. So let's start with week 8 session of complex analysis course. So first of all, I will request those who are viewing me in YouTube for first time, please subscribe my channel. Okay, so let's start with week 8 session. So as usual, we'll talk first what was the important part of the theory which has been discussed this week, and then we'll solve assignment problems. Right. So week 8 is started with the definition of winding number. Winding number. And then open mapping theorem was the second part, or you can call one more result in between, which was inverse function theorem. But that is also very important. Inverse function theorem. And then third was open mapping theorem. And the last was Schwartz Reflection Principle. Maybe there's some spelling mistake. Schwartz Reflection Principle. So we'll talk a little bit about what winding number was, what inverse function theorem was, and what open mapping theorem is actually, and Schwartz Reflection Principle at the end. So Schwartz, with the winding number, what is winding number? Winding number is this defined this way. We fix first. Let's fix the curve gamma. No, starting with a domain. First, let's fix a domain. Let omega subset of C, or because we are not going to talk about any map, so we can just start with a curve gamma. Let gamma be a curve in C, polygonal path or a closed curve. Okay, this was a closed curve. Then we define closed curve in C, and there not be one point in C. We define winding number is written this way: W Z naught winding by gamma. So what is this number? This number is defined by 1 over 2 pi I integral over gamma dz over z minus z naught. So this way, winding number was defined, and there were some results that uh, this z naught is equal to W gamma prime z naught if gamma and gamma prime are homotopic. Are homotopic as closed curve. In C minus Z naught. Okay, there are more results about winding number that it is always an integer for any gamma closed curve. This belongs to Z. And a generalized, at the very end of first lecture, a generalized Cauchy-Gaussian theorem was written this way. Generalized uh, Cauchy theorem. Cauchy. Which is just like it was defined fz not is equal to uh, integral of fz over gamma. Gamma is any curve which is uh, winding z naught once. So here it was one was hidden here, but generalized there comes a new multiple of fz naught, which is this. This is equal to integral over gamma. So z minus z naught dz. So most of the time this value is one. That is why in the actual Cauchy-Gaussian theorem in the uh, previous version, it was not written. So most of the time we take a unit circle as a curve gamma, which has winding number one. Okay. So in example, you just see this. Gamma t is e power I t, and t running from 0 to 2 pi, then it becomes closed curve, and it winding number of 0 by this gamma is exactly 1. We are using Cauchy theorem. And if gamma 1 maybe, or gamma prime t is equal to e power mit, where again t is running from 0 to 2 pi, then winding number is m. This curve, the gamma 1 curve, rotates around 1, not 1, not 2. It actually rounds, winds 0 m times. Okay. So these are some example of winding number, and then inverse function theorem. Inverse function theorem we'll talk about it. This is uh, inverse function theorem. When we have a f holomorphic, let f from omega to c be a holomorphic function such that f prime at z naught is non-zero. Z naught is some point inside omega. Then what happens? There exists a neighborhood u of z naught in omega when f restricted to omega, such that so here such that what happens, the f restricted to u is injective map, and f of u to u, the map f inverse, is analytic. Okay. Or also homomorphism, also holomorphic. What I have written here, this is also holomorphic. Also holomorphic means there exists a small neighborhood where f restriction of f is invertible, and The inverse is also holomorphic. Okay, so this is not true in general for what for real valued functions. Okay, so inverse may exist for real things, but uh, can we find some example of real valued function where inverse is not differentiable? I don't remember right now, but I think we can find some good counterexample which doesn't hold for real valued function. Okay, so f for holomorphic function where derivative does not vanish, there exists a neighborhood of that point. Let's say here it is u, where derivative does not vanish, and f restriction of f to u becomes uh, injective map, and its inverse not on the whole wherever the image is going. Let's say inverse is from fu to u. This is also holomorphic function, complex differentiable, right? So this is a inverse function theorem, and then open mapping theorem. Open mapping theorem. F. So let's start with omega. Omega be open connected domain or open connected subset of C. Subset of C. Then and F from omega to C be complex differential of holomorphic function. Holomorphic. Then F of omega, this image set is open. So this is so as a corollary of open mapping theorem, you just see uh, maximal maximum modulus principle. Maximum modulus principle. So just follow this picture, okay? What is happening? So here you have one complex plane, and here you have some open set omega, okay? And its image is going somewhere where it is open. This is, let's say, F, and the boundary is not here, okay? So I'm talking inside part, interior subset, means fine, boundary is not I'm actually talking about. So if f has, this is our omega and this subset is f of omega, which where it is having image. So what happens? This is open subset, right? And when modulus is maximum, so it's so you make circles of with center at 0. You will find here one point somewhere here. So let's say these are this. I want to make bigger. So this radius, this is maximum modulus. This is a real number. This part, and this is maximum modulus for. So the maximum value here is this point here, lying at this point, right? And because it is open, it is not in the boundary. Okay. So it is in the boundary. So actually it is in the boundary. So the proof is similar. So uh, F from omega to CB holomorphic, holomorphic, then supremum of or maximum supremum of Fz mod plus Z belonging to omega is same as supremum, or now I should write maximum because the Z is going to vary on a closed set, compact set, because omega is a bounded open set, right? Then supremum of modulus of Fz is actually on the boundary, and it is not attained in the interior part. And so the open set is going to open set. So the if somewhere, for example, uh, there is one point here where it attains maximum, right? So it is going to here. This is, let's say, Z, and this is maximum point in the image. This is F of Z. This has biggest modulus inside the image part. Then what happens? This is not an open. Okay. So if it is open, say, okay, the image is open. So this ball, a small ball around Z, is going to have, that is going to be open. And this will give a counter example. Okay. This is contradiction. You see the picture why. So this small ball around Z is going to be an open set, and that cannot lie in the boundary. So there are many points in this small disk which are bigger modulus, bigger than Fz, bigger than modulus of Fz. So that's the contradiction. It is as a corollary, right? So I think it is clear from the picture. So what I mean, no need this much explanation. Fine. What is this? Let omega be symmetric. Uh, Such that, so we partition omega into three different disjoint sets. Uh, Not such that, and let omega be omega plus I disjoint union omega minus. So omega plus is the those complex number inside omega which having imaginary part positive, and this is omega those elements of omega which are having imaginary part negative below the real axis, and this is above the real axis. I is the intersection part with the real axis. Okay, so omega is connected. It always intersects the real axis. And now after this, we now come to theorem. Theorem is this, that if f from omega plus to c be holomorphic and extends continuously to omega plus disjoint union with I, then F can be extended to omega. Okay. So what we define in the below part, below the real axis part in omega minus, you just define the reflection of F. So that is F. So we are going to define new function, extended function with F or G from omega minus to C is equal to G of Z is nothing but F of Z bar. Now see this Z is in omega minus, so Z bar is in omega plus. Now we can it is in omega plus, so we can apply F of Z bar. We are again going to reflect it uh, around the around the x-axis or real axis. So we make it its conjugate once more. And we see that this function is already holomorphic. In some previous exercises, we have seen this. And these two functions, oh, one more hypothesis here, f can be extended to extend continuously to here. And one more hypothesis. So those which are real numbers inside the domain, they are real. F of I is contained in R. Right? I is the intersection of omega with real axis. So I is subset of real numbers. So if f of any real number is real number, then we can extend this function. Extend in such a way that the whole function becomes holomorphic. Extend to omega whole and extension be such that extension uh, map is holomorphic. Okay, so I think we have discussed most of the theorems. We are going to see some proof of them. If you have any doubt, ask by the comments. We'll go to solve some exercises now. I'm very slow, that maybe because we don't have anyone in our discussion today. No problem. We're all going to see these lectures on YouTube. Let gamma be a closed curve around a point Z naught, not in image of gamma. So here, of course, this two closed curve on Z naught belonging to C minus gamma. Okay, pointing number is defined this way. So if it is in the curve gamma itself, we don't define it because the Z minus Z naught is not holomorphic. 1 by Z minus Z naught is not holomorphic in gamma, so not well defined in the domain. Fine. Z naught is not in a point, not in the image of gamma. Then winding number omega is around Z naught is locally constant function. It is proved in the class. Some property of winding number is that it is locally constant. So if a curve, see this is your point Z naught, and a curve winds it once, so there exists, and this is closed set. Curve image of a curve is closed set. So its complement is open. There exists an open ball around Z naught where the curve does not pass through open wall, it is giving the same winding number. The integral of, for example, our omega is t unit disk and z belonging to omega, and curve gamma t is e power it, where t is running from 0 to 2 pi. What happens? Integral over gamma of 1 by z minus w dz. What what I'm going to write? This is not looking like w z minus w dz 1 over z minus omega or w 1 for every omega belonging to d. So we are using Cauchy theorem, right? So where what is function here? This is 1 and evaluated at w. So it is constant function 1. So it is 1. This is just using Cauchy theorem. So for every omega inside unit disk, the unit circle winds it only once. So this is what it means. Locally constant. There exists point neighborhood of the point. T away from omega. Sorry, away from gamma. What I'm telling, my mistake. Sorry. So it is constant function away from omega, gamma. This is not true. So for example, this is also proved in the class that if your point Z naught is lying very away from your curve gamma, so the winding number for this becomes 0. And for interior part, if your Z naught is inside, winding number is some non-zero number, maybe non-zero or 0, it may be 0. How can it be 0? I'll tell you. So it all becomes on what is homotopic. If it is null homotopic or not. If it is null homotopic in C minus Z naught, the curve gamma is null homotopic in C minus Z naught. It can happen. Okay. So you're not actually, so here it looks like it is not null homotopic. How can be in C minus Z naught? How can it be null homotopic? So I'm giving you one curve which will be null homotopic, and you look like it is binding Z naught, but it is not. What? This the concatenation of two curves I'm going to take. The first curve is the circle e power it. Okay. So it starts from 1 and set 1. Okay. And what I'm going to, so the curve gamma 1 is e power it, t running from 0 to 2 pi. So the second, what I'm going to take second curve, gamma 2t is e power minus it, minus it. The t is running from 0 to 2 pi. And now I'm going to concatenate them. So I'm talking about gamma. So the curve is like this. So the first direction is this, reaches up to here, up to 1, and then it returns. Okay. Then after reaching 1, it returns. And it again ends at 1. So where it is, it had started, it ended there. So you see the gamma 1 plus gamma 2, the gamma 1 plus gamma 2, this is null homotopic, is null homotopic in C minus Z, C minus 0. It What is homotopy? Homotopy you can actually define this way. You at every stage t, you go up. So at zero state, you go through go over all the curve. At let's say half state, you go up to here and then come back by the same line. So go this way, come back this way. That's again go up to here and then come back. So the at stage one, what you will do, you will not start and you will not come back. So you are that constantly equal to one. So it is null homotopic in C minus 0 to constant curve 1. Okay, this way it can happen that winding number of 0 for a curve which is looking like it is winding, but it is not actually winding. Okay, so that depends on homotopy, but yeah, this is correct that uh, it is not constant always. For example, unit circle, interior for interior points, what we have, this winding number is 1, or exterior points means points away from the curve gamma, from unit is, their winding number is 0. This is incorrect. So now for part 3, winding number of gamma around Z is continuous function on C away from gamma. Okay, this is fine. The constant curves. So actually this is constant function. So first of all, for C minus gamma, what is this? This is union of a disjoint union of open sets. One of them, so most of them are bounded. One of them will be unbounded, right? So you just see here from a picture, let's say your curve is something like this. So you get 3 components, C1, C2, C3. Okay. C1, C2 are bounded curves, sorry, bounded open sets, and C3 is unbounded component. Open sets, or let's say this joint union of open components. Uh, Maybe one of them is always bounded, sorry, unbounded. One of them is always unbounded. And so in C3, if Z belongs to the unbounded component, the curve gamma is not going to wind it. Okay. So for C3, if Z belongs to C3, what happens? Winding number of Z or a curve gamma is 0. And uh, for this particular situation I'm talking about, Z belonging to C2, what we get? Winding number is 1. And if Z belongs to C1, winding number of Z is -1. So it depends on orientation of curve gamma. So if you see here, it is going counterclockwise. Usually we take this. So and here if you see in this component C1, the curve gamma is going clockwise. So that changes the winding number. Okay, but it is always in an integer, right? So and what, yeah, we are going to see about it is a continuous function. Yeah, of course, yes. Why? Because C minus gamma is disjoint union of open components, and in every component, it is defined to be constant function. So it is constant on every constant functions are on an open set. Constant functions are continuous. Constant functions are continuous in any domain, but here it is open disjoint sets. So they are continuous functions. Winding number is a continuous function. So what are open sets? How many open sets you can get disjoint components? You can get only finitely many components. I think finitely many components. So image of winding number is going to be finitely many numbers. Just like here, we are getting 3. So you are going to get maybe n. So what are open sets in domain side? Finite sets, and their inverse images will be is disjoint union of components, and that is going to be open. So inverse image of open sets are open. So this is continuous function. So image of winding number gamma. I'm not going to write z. This is a function. Okay. This is subset of z. And what are open sets? Open sets. It is finite set. So open sets are finite subsets. And F inverse of minus A alpha of S. A alpha is going to be disjoint union of open sets. So this is open in C minus omega or gamma. Sorry. So it is continuous, and this first part is correct. What about winding number around Z is real valued? Of course, it is integer valued. It is proved in the class. Winding number around Z0 is an integer. Yes, this is correct. So everything is proved in the class, right? So we are not going to why it is integer. Okay, it is done in the class. Go through once more if you want to. Okay, so now coming to second question. Fz is equal to e power z at z is equal to 0. Locally invertible, we're going to check locally invertible functions. So the inverse function theorem is telling when f prime of z at some point is not 0, then there exists a neighborhood of that point where this is bi-holomorphic, means it has inverse and the inverse is also holomorphic. Okay, so how to do this? We are going to check f prime at 0, no? F prime at 0, what it is? E power z, the f prime is again going to be e power z. So at 0, it is 1, which is non-zero. So there exists some neighborhood where it is holomorphic, right? The inverse function theorem. So this is correct. It is locally invertible. Now, what about sine z square? What is f prime at 0? Sine z square. What is f prime? It is cos z square into 2z. we have to evaluate at 0. So it becomes cos 0 is just 1, 2z into z is 0, so it is 0. So this is incorrect. One thing is that in the inverse function theorem, where it was shown that if f prime at some point is non-zero, there exists a small neighborhood around that point where f prime is non-zero. It is because of continuous. F prime is also holomorphic. F double prime is also holomorphic. They're all continuous also. If some are continuous functions where they are not vanishing, they are not vanishing in a neighborhood. So f prime at a neighborhood is non-zero everywhere in that neighborhood, and it becomes a one-one function there, and it becomes actually holomorphic and biholomorphic, means it has inverse and inverse is also holomorphic, and it is one is for if and only if f prime at some point is 0, so it is not 1 1 there. Okay, in any neighborhood it is not 1 1. So it is 1 1 if and only if in a small neighborhood it is f prime is not 1 same. Okay, so we are going to use that, and we are going to we see that the second option is incorrect. What about third option? Here f prime at 0, we are going to calculate it becomes 2 into sin z into cos z. Evaluated at 0, what will become? Sin 0 is 0, so everything is 0. So this is incorrect. Now, in the very same person, what about fourth option, D? F of f prime at z is what? Z minus 2 into 1 minus z minus 1 into 1 divided by z minus 1 whole square, well, z minus 2 whole square. Right. So what is in the numerator? Z minus z, it is 0 minus 2 plus 1, it is minus 1 divided by z minus 2 whole square. So f prime at 0 is equal to minus 1 by, sorry, not f prime at 0. We are where f prime at 1. So it is 1 minus 2 is minus 1 square is plus 1. So it is minus, which is not 0. Hence, the fourth option is correct. It is locally invertible. We are just using inverse function theorem and we are getting the results. Fine. So one thing which I was mentioning right now, the inverse function theorem, the statement is kind of if and only if. Okay, so where f prime vanishes, the function is not 1 1, is very much clear. If it is 1 1, how we are going to say f prime is non-zero? Yeah, sure. There's a mistake. The converse is not true. Okay, you converse true or not? Wait, if f prime is 0, we can't say anything. F prime is 0, it is not 1 1. That is clear. It is the converse of the statement only. So there's not if and only kind of system. But of course, when f prime is non-zero, it is 1 1 in a neighborhood. It is in fact biholomorphic. But if it is 0, f prime is 0 at some point, this is not 1 1. Okay. The proof I can't actually think of how to do. Just let me think. if image 0. So, so this the converse part is true, but if I don't know how to do this, converse part is just like z square. So these two examples are also one of there. Why they are wrong? You look at z square. What did z square does? So see the picture now. Then we'll realize if fz is z square at 0, it is not biholomorphic or it is not one. It is not locally invertible. Invertible. So now we are going to see pictures. What is happening? So it is, let's say, unit disk. This is real axis. Here we have 0. If you have, let's say, 1 by 2 here, this is 1. Minus 1 by 2, sorry, minus 1 by root 2, which is something bigger. And plus 1 by root 2, something bigger. So these two things are 1 by root 2. Where they will go? This is minus, this is plus. They are going to go so minus 1 by, sorry, this is minus 1 by 2. Going to get map to positive in the positive direction. Here, something like this is going to map here, and this is going to map here. This is going to map here. So this is going to map here. So this is 2 into 1 mapping. So we are just looking at local. We are just looking at real numbers. They are going to map to positive side, just like minus 1 by 2 plus 1 by 2. Both are going to map to 1 by 4 this way. So this is not locally invertible. It is not locally 1, 1. So how it can be invertible? Okay. This just from the verification from the picture. We are not going to like uh, all of the proof. Some of them are kind of intuitive. So fine. So this can also be verified that f prime at 0 is what? It is 2 into z evaluated at 0. It is 0. So this way. Okay, now coming to next question. Okay, the third question is about z square. So we already see, we are thinking about this example. Function f is locally invertible at every point in a complex plane. Locally invertible at every point. No, invertible means 1, 1 and undo in a neighborhood. locally means in the neighborhood of every point. But we see that at neighborhood of 0, it is not. At any neighborhood of 0, there is a problem. We discussed above. So this is correct. So incorrect. So what is the problem? This is the problem. Second option is correct. F is not locally invertible at the origin. Okay. Fine. What about third part? Function f is, so what? How to check this? Checking this is fine. F prime at, so f prime z is what? 2z, and f prime z is equal to 0 only when z is equal to 0. So problem is only at z equal to 0. So the part B is correct. So what about part C? Function f is locally invertible at every point in t minus 0. Fine. At every point f prime z does not vanishes in t minus 0 because 0 is already can be removed. What about part D? Function f is invertible in t minus 0. So it's the previous example. This is giving us count. So inside the disk, what is happening? Minus 1 by 2 or minus plus minus 1 by 210, they are going to 1 by n. So this is not 1, 1. So once it is not 1, 1, it is not invertible. Invertible means it has to be 1, 1 and on 2. So this is incorrect. Once it is incorrect, so this is correct. Function f is not invertible in so people are not joining the discussion session. If they will find any problem, they will suffer. Otherwise, we could discuss some of them. There may be, I may be speaking something wrong, which doesn't make sense sometimes. What maybe sometimes I'm telling something and writing something different. So these kind of little mistakes may be there, but in such scenario, we are invited to find my mistake and correct me. The function is non-constant and f is open mapping. Yeah. So again, so I was telling something on open mapping theorem. Omega be open connected subset of C, F be a holomorphic function which is non-constant. C, non-constant. So not in the bracket, it should be P of A. Then F of omega is open. video number 30 or 31, maybe 30. Okay, so the next part is f prime at z naught is non-zero, then there exists epsilon neighborhood epsilon and neighborhood q such that f maps q surjectively onto. Yeah, this is used in the open mapping theorem. This is also a theorem. Okay, so this is used to show that solving all of. In a neighborhood, it can be written uh, some special format where how to write this. So I'm just telling you let let z is f of z is equal to omega. So f of z is equal to w, and in a neighborhood of z, in uh, neighborhood of z, let's say u, f is f of z. So f of z naught is equal to w naught. Let's say f of z is equal to w naught plus I of z to the whole power m, where I is something r for some r. When f applies to this, f applies to this disk. So this disk is uh, gone to the center. It changes from 0 to w naught. So that is what is written here. Okay. So this is correct option. This is a lemma before open mapping theorem, maybe, or lemma. So you just remember a small thing. Okay. So I don't see any problem here. It's probe in the classroom. Okay. Now coming to third part. F of omega is closed set in C. Then f is constant function. What happens if omega is all of C? It is a complex plane, and f is identity function. F is not constant. Still, the image is whole C, and all of C is closed inside themselves because their complement is empty set, and empty set is an open set. So this is incorrect. So the next thing is if of omega is closed, then either f is constant or surjective function onto a complex plane. So the part D is important, where This we are going to solve it. So what are closed subsets in C? Only closed. So first of all, what is only closed and open sets? In C are, so my English is not that good. Not only closed and subset, closed and open sets. Sets which are closed and open are not this way. Subsets which are closed and open both. In C are empty set and C. So f of omega is open by open mapping theorem. And here in the assumption it is given f of omega is closed by assumption. So what implies this? This implies f of omega is either empty set or f of omega is what? All of C. Only two cases, right? So, okay, so there's little mistake. F of omega is open by open mapping theorem when f is constant, not constant, sorry. When f is not constant. So either it is constant or it is not constant. If it is constant, so one case is done, right? So if it is non-constant, what happens? F of omega is open. And f of omega by assumption it is closed. This will imply f of omega is empty or whole of C. And omega is now okay, either it is constant or it is surjective one. It is non-empty. It's just because omega is non-empty subset. So it will be all of C. Fine. Now coming to fifth question. This question is kind of interesting. Maybe I think this question we have already discussed in some previous assignment problem. This is a function of a special kind. But what was the name of this? I don't remember actually right now. Where this function is az plus b, cz plus d, where ad minus bc is non-zero. A special rational function it is. I don't remember right now, but yeah, for this we have seen some exercise problem, the similar statements there. We'll again going to see the same things. So we'll prove them all. Maybe correct or incorrect. I think most of them are correct. So F is holomorphic on an open subset, open connector set, which contains closed unit disk. First of all, this is this function where it is not well defined or not holomorphic when z is equal to minus d upon c, right? Part A. So we are going to see where is the problem. So F is holomorphic everywhere but uh, the set where 1 minus a bar z is 0. This implies where z is equal to 1 upon a bar. So one thing is given, modulus of z is always, sorry, modulus of a is less than equal to 1. A is given from D. A belongs to D. This implies modulus of A is less than 1. So modulus of 1 by A bar. Modulus of A is less than 1, so modulus of A bar is also less than 1. So modulus of 1 upon A bar, this is bigger than 1, strictly bigger than 1. So this implies mod Z is bigger than 1. So where is the problem? The problem is at some point 1 upon A bar, which has modulus bigger than 1. So this implies there's no problem inside D. So problem is in outside D, somewhere, 1 upon a bar. Okay. Now, now I can say second part. Mod Z is equal to 1, then mod let's calculate modulus of F. Okay, what it is? Okay. So this is what I was doing for part B. Right. A into A bar minus A bar into Z minus A into Z bar plus Z into Z bar divided by something which is modulus of A minus A bar. Sorry, 1 minus A bar Z whole square. So what it is? Modulus of A square minus or plus modulus of Z square minus W plus W bar. Is this going to work if mod Z whole square is less than or equal to 1? This is it's not going to work. So something, let's put 1 minus modulus of this. So then what happens? We just want to simplify it more. So we have to multiply here 1 minus A bar Z, 1 minus A into Z bar, and minus everywhere inside. So minus here, plus here, minus here. So it is in the numerator. And we further simplify this. So this is 1 minus A bar Z minus AZ bar plus mod A square Z square, mod Z square minus this is, now I'm going to write the already written part in previous thing. So this is mod A square plus A bar Z plus AZ bar minus mod Z square. So this this two get cancelled. So what remains is this 1 minus mod A square minus mod Z square plus mod A square into Z square. In the denominator, what we have? 1 minus A bar Z whole square. 1 minus A bar Z whole square. Yeah, further in the next line, what we're going to take common 1 minus A square, 1 minus mod A square. So here from the first place you get 1. From the second place you get minus Z square, minus mod Z square. Yeah, correct. 1 minus A bar Z whole square in the denominator. Plus. Okay, so up till this, what you know, where Z belongs, where A belongs. So in the question, So now when mod z is equal to 1, what happens? So up this calculation, this let's say this is our star. Mod z is equal to 1 implies this value is 0. 1 minus mod z square. This value is 0. So 1 minus mod fz whole square. This is 0. This implies mod fz is equal to 1. Okay. So the second option is correct. Now what about third option? When mod of z is less than or equal to 1, what happens? Mod of z is less than or equal to 1. What happens? This value, first value, 1 minus mod a square. This is anyway less than 1 because mod a is belonging to unit disk. And 1 minus mod uh, z square. This is also less than 1, right? So their product in the numerator, that is less than, that is less than 1. And all of them are positive. So the right side is RHS of star is positive. This implies 1 minus mod of z whole square. This is bigger than or equal to 0. When z is strict, this is strictly bigger than 0. So in this scenario, what happens? Mod of fz whole square, this is bigger than 1. This will imply mod of fz is bigger than 1. What is there in mistake? So yeah, what we are going to do? Mod of fz is less than or equal to 1. The mod of fz is less than 1 or bigger than 1. We have to check. Fine. When right side is positive, what happens? Here is little mistake. So when this inequality, now the next inequality will be 1 bigger than mod of f whole square. This will imply 1 is strictly bigger than mod of f. So the part C is also correct. Boundary is going to boundary. The second part implies interior is going to interior. The third part is implying for unit is. The image of FD is open subset of omega. Because function is non-constant, it is open because of open mapping. Function f maps D to D. How to check this? F maps D to D. We have just seen that F maps D inside D. This boundary to boundary, interior to interior. Is this onto? Is this 1 1 or not? What about F restricted to D? What happens? So let's see. We know here part 3, part, part 1 minus F is nothing but what is this? A minus F. A minus A divided by 1 minus A bar into then what happens to F square Z? F composite F Z. This means F composite. So this is F of A minus Z divided by 1 minus A bar Z. So we put this A minus Z 1 minus A bar Z divided by 1 minus A bar A minus Z divided by 1 minus A bar Z. We calculate this, what happens? A into 1 minus A bar Z minus A minus Z divided by 1 minus A bar Z minus A bar A minus Z. So 1 minus A bar Z cancels right and downside. Further solving this, what we get? A minus what A square Z minus A minus Z. Here 1 minus A bar Z minus what A square plus A bar Z. So plus A bar Z minus A bar Z get cancelled. A and minus A get cancelled. Z is common, so Z what remains inside is so this is actually plus Z minus 1. This is plus Z common, it is 1 minus what A divided by 1 minus what A. This is equal to Z. So this implies F is self-inverse. This map is having itself, inverse is itself. So what happens? Inverse. This is also holomorphic, leaving 1 point where 1 by A bar, and it is having self-inverse. So it is 1 1 or 2. So the map is bijection on what? This implies F is invertible or 1 1 or 2. C minus where the 1 minus 1 divided by A bar, and T is contained here. This implies T is F of D is equal to yeah, that's it. That's that's it for today. We'll see you next week. Maybe join in the live session. Ask you doubt. See you next week.